Oh, yay! I was hoping you were going to stop by. Hey, while you're here, let's go ahead and talk about patterns and nonlinear functions. So our main objective for right now is to identify and represent patterns. So we're looking for these patterns that are happening that describe a nonlinear function. So these are still functions, but there's something about them that makes them nonlinear. And a nonlinear function is one where it is a function, but the graph is not a line or part of a line. Okay, so there's something going on here where there's this missing this straight line element to it, like in this particular situation here with wood. But we're gonna practice a few things out here, and let's wrap our head around this one. So linear functions, because a linear functions whose graph is non-vertical, it's a non-vertical line. So we're saying like this, okay? That's a vertical line, and that is not a function, so not that, so non-vertical, or part of a non-vertical line. So these guys are all functions, nice straight lines here, here, and here. Non-linear functions, okay, so these are still functions, but they're not linear. We got a curved line, we got something curved, we got a straight line, but this one V is a little bit different. It looks like a V, and that is also not linear. It's made up of two straight lines, or it's a part of a straight line. So let's try this out. Classifying functions as linear or nonlinear. Okay, so here's two situations, or one situation with two things happening here, and we're going to take a look and see what we can determine if something is linear and nonlinear. The area A in the square inches of a pizza is a function of its radius r in inches. That's just saying that these are two variables that are happening and there's a relationship happening between them. There's the function. As one changes, so does the other. The cost in dollars of the sauce for the pizza is a function of the weight in ounces. It's simply saying there's a function, there's a relationship happening. As one changes, so does the other. That's what's happening with that word function. Graph these functions shown by the tables below. Is each function linear or nonlinear? And that's what we're looking for. So we have pizza area and sauce cost. So let's take a look at these. We've got the information up here as radius and area, and then we've got the weight and the cost. So I'm going to keep moving down. A couple things we know is the relationship between the tables. They are functions because they tell us they are. We need to classify them as linear or nonlinear, and we're going to use the tables and graphs to help us with that. So graph A, let's take a look at this. Okay, so graph A as a function of radius. So first thing we got to do is determine what's going on here. We're going to use the vertical axis for the area, because the area is our dependent value. How much pizza we can make really is depending on the radius, okay? The area of the whole pizza is really dependent on what the radius is. Once I know the radius, I can calculate the area. And that's why we say this one depends on this one. And once I have that, I can go ahead and take my different piece of information and plot it out. And there is my graph. It looks like it's a bit of a curve to it. And because it has a curve to it, we can say that it is a function, but it is a nonlinear function. This one is not creating a straight line. Let's look at the sauce cost. Okay, so a couple different pieces here. We have the sauce and we have the cost in dollars. And it would make sense though. The cost really depends on how much sauce I use. How much do I charge for this is really going to depend on how much I have. So that's why sauce is my independent variable and cost is my dependent variable. And when I graph this out, nice straight line, and that tells me that it indeed is linear, that this function, that this relationship is a linear relationship. Okay, so a couple things you got to do is figure out where your variables go, if they're dependent or independent, and usually you kind of got to look at that conversation. All right, here's a got it, and I want to see if you got it. So go ahead and press pause and work it out and see how you did. Make sure you grab some graph paper too and graph it out. Don't just watch me do it. I want you to be able to do it. Ready, pause. All right, this is what we got. And it looks like it's this nice curving relationship going on here, and because it curves, it is not linear. And the question up here is asking me, will the area A in part ever reach zero? It will not reach zero. It can't reach zero. There'll never be a place where we don't have any cuts of pizza. We're just going to keep cutting it and cutting it and cutting it, but it'll never reach zero. It does seem like it though when you first look at a graph, because most of the graphs we've seen do move until they get to zero, but not this one. Let's look at this guy, representing patterns and nonlinear functions. Okay, so we're looking at a cube here, and so one block. And actually, figure 1, you can look at it that. So figure 1 ends up having 1 block to it. Figure 2 right here, and that's going to have 8 blocks that make that up. Figure 3, if we can look at that one, and that's going to make up 25 blocks. So, and you can see where it's coming from. There's 1 on this face, there's 2 here, and there's 3 here, and that's where we're getting our numbers from. And we're going to also work on 4 and 5. So if we keep looking at these, the next 2 figures that we have, 4 is going to have 4 on the face, right there, and the 5th one is going to have 1, 2, 3, 4, 5 on the face. The total number of blocks that's going to happen here in my, if I have 4 on the faces, there are going to be 64 total blocks that make this up. That's a lot of blocks. And because of that, I can do my ordered pair from it. Just like at the top here, I can do, if I'm looking at my edges to my total blocks, I can come up with the coordinates 1, 1, which I got here. And I can have the coordinates 2, 8. Because I want to graph this. I want to take a look at the relationship. So it's 327. So it's going to be 4, 64. It's going to be 5 and 125. And I've got these coordinates now, looking for a relationship between them. A cube with 4 blocks on the edge contains a 4 times 4 times 4. It's our 64 blocks. So that's where we're getting our numbers from. So I finished my table. Okay. Now the words. This is how I want to communicate this, and you want to get in the habit of writing a sentence to describe what you're seeing. And this is the sentence. The total number of blocks y, that's coming from here, the total number of blocks y is the cube, that's this, times itself 3 times, the cube of the number of blocks on one edge, x. So if I know the number of blocks on one edge, I can cube it to get my total number of blocks. That's what it's saying. And my equation looks like this. Y equals x cubed. You could use that table to make a graph. The points do not lie in a line, so we're going to take a look at that. And it's curving upward. And we can say that this is a nonlinear function because it's not a straight line. It's curving a bit. All right, this one I want you to give a try. We're looking at branches of a tree. So you're going to do a few things here. You're going to represent using words, an equation, and a graph. Okay, but you got to fill out the table first. So do the table. Write a sentence describing the relationship that's happening. Write an equation of what's happening, and then graph it out, and that will let you know, are you looking at a linear or a nonlinear relationship? Go ahead and press pause now. All right, the number of branches is 3 raised to the x power. I know, who would have thunk that? But that does happen though. So we can see that it's 81 and it's 243. So this thing jumps like crazy. And I got to imagine even the one after it jumps even more crazy as I do 3 to get this number right here to get the 6th figure. I'm going to go ahead and do, what is that? That's going to be like 3 to the 6th power. 3 times 3 times 3 times 3 times 3 times 3. That's going to be a really big number. So be paying attention for the relationship, looking for the pattern. Sometimes it is an exponent. Again, not linear. Let's look at one more here. A function can be thought up as a rule that you apply to the input in order to get the output. Okay, that is our input and output function machines. You can describe a nonlinear function with words or with an equation, just as you did with linear functions. So you can do that. So we're going to describe a nonlinear function. So we have these ordered pairs, 1, 2, okay, and here's 1, okay. And what I need to do is I'm going to first look at it and try what rule produces a 2 when given a 1. Okay, and I've got a couple options here. I can, 1 doubled is 2, so it could be that one. My x term, 1 plus 1, gets me 2, so it could be that one. And I also got this one with a base of 2. So 2 to the x power, so 2 to the first power is 2. So that might be it. Okay, so those are my 3 choices. Now if I look at something else here, I look at my next coordinate, which is 2, 4. I'm going to see which ones work. And I'm noticing here that 2 plus 1 doesn't work, so that's out. 2 doubled does work, so that's in. okay? And a base of 2 to the x power, so 2 to the second power, so I'm looking at this guy. 2 to the second power is 4, so that works. So this one's still in, and this one is still in. When I check it on 3/8, I see that 3 doubled is 6. It's not 8. So now doubled is out. But I'm going to look at and consider if the base is 2. So if my base is 2, and my exponents, whatever is in the x term, which is the third, so it's 2 times 2 times 2, that is 8. So that one still works, and that's in. So if I try a couple of these other ones here, let's see if we can do this. That would be 2 to the fourth power, and that is 16. 2 to the fifth power, which is 32. So that is telling me that my rule for this one is going to be y equals a base of 2 to the x power. And so I have my rule for that. All right, here's your got it. Why don't you go ahead and press pause and you try it out. Okay, first of all, you put them into a table, okay, and you plotted out your x and your y. So you did the 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. So tried all these different things, tried adding things, doubling things. I hope you tried a few different things, and hopefully you recognize these numbers. These are perfect squares. So hopefully you found that. I take my x term and square it. So I take whatever my x is, and I square it, and I'm going to end up with my y term. All right. Excellent. Well, thanks for hanging out with me. This was a good time. I'm going to go chase a zebra until my face hurts.